What is angular velocity? In this section of the trigonometry course, this is either the first time or close to the first time that you've heard this term angular velocity. Okay, so since this is an introduction to this concept, in this section we focused strictly on a simplified application of angular velocity. So here is the simplified application. We have an angle theta measured from standard position, right? So the horizontal x-axis, and then you draw a terminal side somewhere in the Cartesian plane, and that terminal side represents an angle theta, okay? But in addition to that, the terminal side is specifying the location of a point or an object or something to where that point or object its motion is constrained to a circle of radius r. Okay, and so as you just heard, this is a little different than what we've been doing so far up to this point in the course, and that we're thinking about this point P here is something that is moving. It's in motion with the motion restricted to a circle. Okay, so again, this theta is mapping the position of a point somewhere on a circle. Now, since this point is in motion, what you can think about is the angle theta is actively changing. Now, if you take a certain time interval, say when the point P goes from here to here, that takes a certain amount of time, and then going from here to here, there's this certain angle, whatever, alpha or something. If you divide the amount of angle that it covered going from here to here, divided by that time it took, that's angular velocity. That's its angular velocity. And since the angular velocity is constant, you could do this procedure here with, you could take point P going from here to here. That's a certain amount of time. So divide the amount of angle that is divided by the time. You do that for any distance. You could go from here to here. You could start with point P here and go to here. You're going to get the same value for the angular velocity no matter what, because the angular velocity is constant. But that's what angular velocity is. It's an angle traveled, or an amount of angle covered, divided by the time it took to cover that angle. That's angular velocity. Now, the textbook contrasts angular velocity with what it calls linear velocity, and it's kind of confusing because when you hear the word linear, you think motion along a line, but what they're referring to is not linear velocity, but the classic definition of speed or velocity that we know of, from when we were kids. The first idea of speed or velocity that you become aware of growing up, that's what they mean by linear velocity. So what does that mean? How is that different from angular velocity? Well, okay, any rate of change, the rate of change of anything, no matter what it is, the rate of change of food, the rate of change of, it's any rate of change it's like the change in some quantity. So here we had like a change in angle going from here to here, or the change in the amount of food eaten or something. The change in some quantity with respect to time. That's what a rate of change is. You can call that a speed or velocity, etc. The classic speed or velocity that we're familiar with is the change in position with respect to a time. So in other words, like a length divided by a time, meters per second, miles per hour, right? It's some distance. If you're running along a track, someone's running really fast. They're covering a lot of distance with respect to a certain amount of time. Okay, and so the textbook's calling that linear velocity or linear speed, but I'm not sure how much I've heard of it being defined that way. Because, okay, so we're going to use this idea of linear velocity in this problem here. Why? Because we can think about this mass or point here has a quote-unquote linear velocity. Of course it does, because it's, so when this went from here to here, okay, over this angle alpha, that was a alpha per the amount of time it took to go from here to here. It has an angular velocity, but it also covered a certain distance. And there's an arc length here. We'll call this x in that time. So you take x divided by that time. That's it's what the textbook is calling linear velocity. I don't want to use the term linear because this is not linear, right? It's just they're referring to the classic distance per time definition of speed. Okay, so, but if the angular velocity is constant, what does that mean about the regular velocity or the speed? Maybe I'll just say speed or when I just say speed or velocity without any, description of what it is, like angular, or etc. I'm talking about distance per time, like the classic definition. So, what is the fact that the angular velocity is constant? Does that mean that the velocity of the particle is constant, the speed of the particle? I don't know. That's interesting. Okay, and so this application here of angular velocity with regards to circular motion it's a very common application of angular velocity. A lot of times if you're using angular velocity for something, to study something or to model something, whatever, in practice, whatever, a lot of times it's going to be you're looking at circular motion. So whether it be a car driving and then it gets to a curve, right? Well, that curve it's a radius of a circle. So the car is driving around a circular arc, or gears, pulleys, right? The speed of a conveyor belt. You could relate that to the speed that the engine is turning the wheel, and then if you can relate the velocity at the tip of the wheel to like an angular velocity, you can get the speed of the conveyor belt, for example. Okay, so let's go ahead and derive all of the equations that are associated with analyzing a system like this. We went through these equations in the textbook section, but you really shouldn't have to memorize these. These are easy to derive. Okay, so you don't have to work in radians, but it's much simpler to do this with radians. Okay, so we're going to work in radians. Let's just start with an equation that we actually learned before this section. We know that S is equal to R theta, assuming that theta is in radians. And this is universal. I mean, if theta could be negative, we'll get a negative S. Yeah, we can have a negative velocity, right? If we have a negative velocity, then we're rotating in not this direction, but the other direction. And just when theta is equal to 0, we're at that means S is equal to 0, that means we're here. Or when theta is equal to, something greater than 2 pi, we might be here, but we know that we've rotated a certain number of rotations, and then we got here. So if you input theta and multiply that by R, you could get the position of the point P, whatever that is, some mass, a particle or something. Okay, now let's just start with the idea of angular velocity, which the symbol is omega. We know that's going to be so if we think about that at time t is equal to 0, the point P is at B. And then when the time starts, that's when theta starts moving with a constant angular velocity in the positive direction. That's the idea here. That's what's happening here. So again, at time t is equal to 0, P is at B, theta is equal to 0. You start, and then theta automatically has a constant angular velocity. That's what's going on. Okay, so what is the angular velocity of theta? Well, in that case, it's just going to be whatever theta is divided by the time. We're not going to put like a delta t, like a change in time or a change in theta. It's just going to be whatever theta is divided by whatever the time clock says. That's the angular velocity. Okay, now what's the velocity, the linear velocity, whatever you want to call it, of the point? Well, it's the distance it moves. That's just v. It's the distance it moves in a certain amount of time. So that's going to be s divided by t. Okay, and so that's really it. These are the main equations you use to analyze the system, but further, you could go further And you could say, okay, so V is equal to, what is S? S is r theta. There's another equation. Okay, but look, what is theta divided by t? That's omega. So that's how you get V is equal to r omega, right? So there's no need to memorize these. I mean, if as long as you know what angular velocity means, theta divided by time, and what regular velocity means, the position divided by time, then, you know, this is, to get V is equal to r omega, that's easy. Now, whenever you're working a word problem on something like this, it's helpful to keep the units of these in mind. So, okay, the angular velocity, if you're in radians, okay, angular velocity is going to be, that's theta is radians. Time is in, you know, it doesn't, seconds. We'll just say seconds. It doesn't have to be seconds. We'll just say seconds. But remember, radians are unitless. So technically, omega is in 1 over seconds. That's the units. If we were in degrees, we would have to put degrees per second. With radians, these are technically unitless, the radians. So it's just 1 over seconds, also known as hertz. This is also known as hertz. Okay, but it's important to remember that radians are unitless, because if you want to get a velocity, a classic velocity, well, think about it. Radius times omega. Radius is a length, right? Well, if you multiply a length by 1 over seconds, you get meters per second, centimeters per second, miles per hour, right? You get what you expect for a velocity, a distance per time. And then, but here you also get what you expect, a distance arc length per time. Just like here, since theta is in radians, unitless, a distance, a length, r times something unitless gives you an arc length as a distance. Okay, so like if you have omega, let's solve for omega here, V divided by r. What is this? That's, so velocity, let's say it's like meters per second divided by meters per second times just unitless over time. That's omega, at least when you're dealing with radians. Okay, and you can play with this. So, okay, V is equal to r omega, V is equal to S over T, so that means r omega is equal to S over T. So S is equal to r omega T. That's interesting. You know, you can play with these relations. Okay, now it's important to note, though, that we are focusing on a simplified case here of an application of angular velocity, just for the sake of introducing the concept. So, in other words, when you think angular velocity, you don't have to think about a circle. It's this. So the general definition of angular velocity is you go to the definition of the angle. So you have a vertex here. You could draw a straight side here, and then another straight side here. The lengths don't matter at all, just that they're straight and they have this vertex, this common vertex point. And then the opening between the two, the opening in the sense of the amount of rotation to go from one side to the other, rotating about the vertex, that's the angle theta. Okay, so the rate of change of, if theta was changing, then its rate of change with respect to time, that's the definition of angular velocity. Okay, so there's no circle here, right? So what I mean is that what you can think about like a planet orbiting the sun. They're like elliptical orbits. Okay, well, let's say the planet goes from here to here. Even though these lengths aren't the same, you know, this is R1, R2, whatever you want to call it. This is some angle theta. Well, you could think about there's the rate of change of theta with respect to time. That's an angular velocity that's associated with the position of this planet. And we saw that it ended up being the case that, so V is equal to R omega. That was the velocity of the point. That was, since omega is constant and the radius is constant, the velocity of P is constant. So it ended up being the case that, yes, if the angular velocity is constant, then the corresponding circular motion, the velocity of the the associated particle or point or mass is also constant. But that might not be the case for something like this. Maybe the actual velocity of the planet is, if theta is not constant, or if theta is constant, maybe that the velocity is not going to be constant. Maybe the velocity is a function because the radius I guess you can call it a radius, since that's changing, it's a function of this distance, since that's not constant, right? But even so, that you're still dealing with an angular velocity. It's just a more complex system. It's interesting to think about for an elliptical orbit. If theta is constant, what does that mean? Then what is the velocity dependent on? Is the velocity constant, or is it dependent? I'm assuming it'd be dependent on this. Since theta is constant, it's dependent on since the omega is constant, it's dependent on this distance here. Or if the velocity is constant, then what does that mean for the omega of the angle? Okay, but it's any application. So, we think about, you could have like polar coordinates. We're going to learn about polar coordinates later in this course, but the polar coordinates use an angle so let's say there's a mass here. One of the coordinates for polar coordinates is like a radius and an angle, okay? So like radius meaning this is r. R can change, okay? But when you go, so here's R1 and here's R2, and then there's an angle associated with each of these, theta 1, theta 2. The rate of change of the angle is that's another angular velocity. Angular velocity is the change of angle with respect to time. That is what angular velocity is. It is not married to circular motion, even though, again, that is a very common application of when you'll use angular velocity.